Hey everybody, welcome back, and we're going to continue reading about recursion. It is perfectly okay for a function to call itself, as long as it doesn't do it so often that it overflows the stack. A function that calls itself is called recursive. Well, there you go, that seems like a definition. To be sure, I also added another piece to our vocab list. The coding example from a closure, the one with the multiplier, I've added that into the code examples. And let's go ahead, and a function that calls itself is called recursive. Eh, Recursive. I know we're not following a lot of the traditional rules for definitions in terms of not including the word in the definition, but these aren't really definitions. They're quick references to help you learn these terms and be able to use them in practice. So um, that's my hacky solution for that. So a function that calls itself, some functions. We'll leave it as that. So recursion allows some functions to be written in a different style. Take, for example, this alternative implementation of power. Function power takes two, come on now, parameters, base and exponent. If exponent is equal to 0, and we're going to change this to triple equals because I don't mess with double equals. If exponent is equivalent to 0, return 1. Otherwise, return base times another call to the function, base times exponent minus 1. I would recommend thinking about this thoroughly. And I could explain it to you what's going on here. And as we move further through this section, we'll explain all these things fully. One of the things with recursion, though, is that it is a different way of thinking than the iterative fashion, which is to say looping. And you're really going to be best served by just thinking about it carefully over and over again over significant portions of time. If you look at this and you don't get it the first time, congratulations. You and 85% of the people that will look at this kind of hit the same wall. Most of the people will climb over that wall, though, to become developers, because recursion is among those topics that are kind of bread and butter for coding interviews and technical interviews and things like that. Most coding boot camps probably won't want you to, or won't need you to know recursion, as like a pull it out of your bag of tricks, during the interview. But generally, recursion comes pretty quickly because it's a fundamental computer science principle. So with that in mind, let's just make sure this works. It does. This is rather close to the way mathematicians define exponentiation and arguably describes the concept more clearly than the looping variant. I've actually never thought of that, but perhaps that's something to consider as well. The function calls itself multiple times with ever smaller exponents to achieve the repeated multiplication. But this implementation has one problem. In typical JavaScript implementations, it's about 3 times slower than the looping version. Running through a simple loop is generally cheaper than calling a function multiple times. The dilemma of speed versus elegance is an interesting one. You can see it as a kind of continuum between human friendliness and machine friendliness. Almost any program can be made faster by making it bigger and more convoluted. The programmer has to decide on an appropriate balance. That's honestly why we talk about engineering as opposed to just programming. Engineering tends to, help one balance those considerations, let's say. In the case of the power function, the inelegant looping version is still fairly simple and easy to read. It doesn't make much sense to replace it with the recursive version. Often, though, a program deals with such complex concepts that giving up some efficiency in order to make the program more straightforward is helpful. Worrying about efficiency can be a distraction. It's yet another factor that complicates program design, and when you're doing something that's already difficult, that extra thing to worry about can be paralyzing. Therefore, always start by writing something that's correct and easy to understand. If you're worried that it's too slow, which it usually isn't, since most code simply isn't executed often enough to take any significant amount of time, you can measure afterward and improve it if necessary. Recursion is not always just an inefficient alternative to looping. Some problems really are easier to solve with recursion than with loops. Easier to solve with recursion than with... I don't know why, but that sentence feels awkward to me. But that's okay. Excuse me. Most often, these are problems that require exploring or processing several branches, each of which might branch out again into even more branches. Consider this puzzle. By starting from the number 1 and repeatedly either adding 5 or multiplying by 3, an infinite set of numbers can be produced. How would you write a function that, given a number, tries to find a sequence of such additions and multiplications that produces that number? For example, the number 13 could be reached by first multiplying by 3 and then adding 5 twice, whereas the number 15 cannot be reached at all. Here's a recursive solution. So we've got a nested function. Find solution, we're taking in a target. Function find is going to have a current and a history. If current is equal to the target, return history. Else if current is greater than target, return null. Else return find current plus 5. And what do we got here? Okay, so we're interesting. I don't think I've ever seen that before. So it looks like it's a string where we're passing in the history, or interpolating the value of history into a string that's going to be that plus 5, or multiply by 3, and we, I guess, pass the history in, multiply by 3. I don't understand this, but that's okay. Most of the time, when you look at things the first time, you might not understand them, but it's always a good idea to stick to your principles. So what are our principles? Because we might not have listed them yet. Our principles are, well, we're going to read everything first before we decide that we don't understand something. I guess we should probably run something. And okay, so let's get a little bit better, like a cleaner idea of what's going on here. So at a certain point, it's going to return some string. And the reason that I know it's a string is because I can write type of here, provided I spell it correctly, run it again, and now I know that the solution, or the output of find solution, is going to be a string, which that helps. And return 1, history is 1. Okay. Still don't know that I completely understand this, but that's okay. Note that this program doesn't necessarily find the shortest sequence of operations. It is satisfied when it finds any sequence at all. It is okay if you don't see how it works right away. Reading does it again. Let's work through it, since it makes for a great exercise in recursive thinking. The inner function find does the actual recursing. So that's this function here. The inner function find does the actual recursing. It takes 2 arguments, the current number and a string that records how we reach this number. Okay. If it finds a solution, it returns a string that shows how to get the target. If no solution can be found from this number, it returns null. So let's go ahead and write a piece of pseudocode here, because it sounds like what this line is doing, excuse me, if no solution can be found, then we return null. So in the case that we return null, that's current is greater than target. So essentially that just means if current is greater than target, then we know no solution can be found. All right. Find solution, returns null. To do this, the function performs one of 3 actions. If the current number is the target number, the current history is a way to reach the target, so it is returned. So that makes sense. And that's this piece of pseudocode for this piece right here. Let's go ahead and make sure we write it. If the current number is greater than the target, that's not the one. If the current number is the target, it's returned. Well, this is the sentence. So what we're going to do is we're going to take a sentence, we're going to pare it down to pseudocode. Because as you can see, it's kind of awkward the way it is. It takes a long time to read it. So we'll say, if the, seems like a superfluous word, so we'll say if current number, current is going to be anything other than a number, so we'll get rid of that, is the target number, so we'll say equals, and then again, target is never going to be anything other than a number. So if current equals target, we've already shortened it a little bit, current history is a way to, and current history, this is one of those where pseudocode cannot be just the sentence describing it in all cases, because current history and current are going to be 2 completely different things. Current is the number that we've gotten to. History is the way that we got there. So to say the current history, while the current in the current history phrase means something different than current here, that means we need to lose it. Because if we're talking about something, we can always just assume that it is the current value. We could say past history or future history, and that might help us delineate, but for now, history is probably going to get us there. So history is way to reach the target. History is the result. And history is the result is basically a way to say history is returned. So there we go. If current equals target, history is returned. In general, we might say something like return history, because the same way that the same way that code kind of describes what it should do, pseudocode should do the same thing. So rather than saying history should be returned, we'll say return history, because we are let's say, personifying control in the program. All right, cool. So to do this, if the current number, the target number, current history is weighted with target, it's returned. Excellent. If the current number is greater than target, there's no sense in further exploring this branch because both adding and multiplying will only make the number bigger, so it returns null. Now we already did that. If the current is greater than target, no solution can be found. Let's shorten this up. We'll say return null. Now, I've heard people say that this return null part probably describes this piece of the pseudocode, but that's okay. So where we at? It returns null. Finally, if we're still below the target number, and that's going to be the else portion here, so we'll say if we are still below the current number, and what that essentially means is, let's think about this. Current is equal to target, current is greater than target, means that the only thing left is if current is less than target. And that means that we can get rid of all of this. So if current is less than target. Perfect. Where'd it go? Finally, if we're still below the target number, the function tries both possible paths that start from the current number by calling itself twice, once for addition and once for multiplication. If the first call returns something that is not null, it is returned. Otherwise, the second call is returned, regardless of whether it produces a string or null. And that's kind of cool, right? Remember the whole short-circuiting thing? Essentially, if this returns a value that is going to be truthy, we're never even going to evaluate this part of the function. Or sorry, this part of the expression. And by expression, we mean this guy right here. That's the expression. If the first part returns a truthy value, the second part isn't evaluated, which means that this function call doesn't even happen. Which is nice, right? So let's go in here and try to figure out a way to describe what's going on here. So we'll say tries both branches, first add 5, then multiply by 3. That's probably the most inelegant version of pseudocode we've written so far, but it's a good little reminder. Another fun part is that you can always just scratch your code or your pseudocode and start over from scratch. And every once in a while, well, I guess you wouldn't scratch it and start over from scratch. Or maybe that's exactly what you would do. Anyway, finally, if we're still below the target number, the function tries both possible paths that start from the current number by calling itself twice. The first one, otherwise, excellent. So, to better understand how this function produces the effect we are looking for, let's look at the calls to find. Let's look at the calls to find that are made when searching for a solution for the number 13. So we start with find 1 and 1, and that's here. So we'll say return initial call to find. So we got find 1 and then a string of 1. Find 6. So what happened there, if we go find with 1 and 1, current and history, so we'll say is the current equal to the target? And the current is going to be 1, and the target is going to be, I think it said 13. So one of the things that they're not putting here is that we are calling, where's it at? Find solution with 13. So what's going to happen is that we're going to first check to see if current is equal to target. Current is 1, target is 13, so that doesn't work. Otherwise, current is greater than target, 1 is not greater than 13. Else, find current plus 1, history, plus 5. I have no idea how to read this out loud. It's like the string version of the current history plus, oh, I said current history again. So a string version of the quantity of history plus 5. So it's essentially recording what we're doing here into the history. Okay. So find 6, and then the history of 1 plus 5 has now been, find is being called with that history again. So essentially, it's this call to find that's happening. So this call to find, we jump back up and we enter into another version of find, which is to say find is being opened up again. This time current is equal to 6, and the history is this little string here. So if we look at 6, well, it'll be down here. So if we look at 6, it looks like 6 is going to be, what is it called? 6 plus 5. So we got 11. And that adds this to our history. And then we find 16. 16 is too big. So here's what happens when that is. That's a call right here, but we get back null because we basically make it to here. else if, and then current at that point is 16. 16 is greater than 13. So what happens is that this part of the call, inside of this call right here, that becomes null. And that was the case that we were describing where if that becomes null, then this part operates. So current times 3 is 33, which is also too big. Now, here's the crazy part. This is actually going to be, if you can trace it, inside of which call? It can be a little bit, well, annoying to try to do this, right? Because what we're essentially finding at this point is that 6 multiplied by 3 is also too big. So the part here is going to return null from this part. Oh, wait, I did that wrong. 6, 5. Oh, I don't like these indentations. Oh, I think these indentations are off by 1. Because theoretically, I would like to see this indentation, basically all of this, move back 1. Because what we're essentially doing is we're going from here to here. Oh, you know what? The indentations are fine. Never mind. I'm making a mountain out of a molehill. So essentially, we try this route, gets us all the way down to here, and there's no version of those branches that ends up with a correct answer. We get too big in all cases. So if that's the case, rather than adding 5, which is essentially this entire branch has ended up in all of these too bigs. So all the way down to here, we basically returned null for all of the options. So what happens then is that this entire call from the very first iteration returns null. So we try this one, multiplying by 3 first. When we multiply by 3 first, the history becomes this. We add 5, the history becomes this. We add 5 again, the history is now equal to the final result because our target has actually been found. So we give back this. Now, if that was confusing, it's because I'm not that good at explaining recursion. But being able to explain recursion and being able to understand it are kind of linked. So it's always good to try to do as much explanation as you can. I would suggest, they call it rubber ducking, but there's, plenty of different inanimate objects, or animate, if you're lucky and you have like a kid hanging around, or a dog, or cats are pretty good, because cats tend to give you the sort of supercilious look that requires one to think deeply about one's actions. Dogs tend to be excited about whatever you say, so even if you tell them an incorrect way to do a recursive solution, the dog's probably going to be all about it. So, the indentation indicates the depth of the call stack, and does so correctly despite my thinking that it didn't. The first time find is called, it starts by calling itself to explore a solution that starts with 1, 5, and that's going to be here. That call will further recurse to explore every continued solution that yields a number less than or equal to the target number. Since it doesn't find one that hits the target, it returns null back on the first call, and that's going to be this one. This is getting back null because all of the eventual all of the eventual ends of the branches that we examine get us numbers that are too big, either by multiplying by 3 or adding 5, which is, of course, to say after the first initial adding of 5. So it starts 1, 5, every solution. Since it doesn't find one that hits the target, it returns null back to the first call. There's an OR operator. There should be a comma there. There, the OR operator causes the call that explores 1 times 3 to happen. And that's this one right here, which again is correctly indented. This search has more luck. Its first recursive call through yet another recursive call hits upon the target number. What they're essentially saying is that we added 5 here, which recurses again because 8 is not equal to the target and not greater than the target. So it comes to here, does the first one, which is adding 5, and then actually gets 13, which is the target. So when we get to this part, current is equal to target. Current has now been made to 13, so the history that we've been storing gets returned as well. Oh, it gets returned as the solution. That innermost call returns a string, and each of the OR operators in the intermediate calls passes that string along, ultimately returning the solution, which is essentially, that's this part. So when we return this or something, and this part that we've highlighted ends up being this history string, it gets returned up the whole chain. And by chain, we literally mean here to, from here to here to here to here, and then here. And you want to think about that because this find 1, 1, this value that's being returned for this function call is essentially the return of our function. That's hopefully this is starting to make a little bit more sense. If it's not, time and patience is your best friend. Okay, returning operators, intermediate solution. And I think that this is another H2. Yep, that's another heading for a section. So that means that we're done with recursion, but not in the long term, just for the section. Thanks for watching. Hope you enjoyed it. At this point, well, let's go ahead and grab this piece of code with our little, our comments. And we're going to copy this and put it into our editing closure. We'll say a recursive solution. Okay. So that's a good example to hang on to. Other than that, we're going to jump into something new. Well, maybe not new, but we're going to jump to the next section in the next video. Thanks for watching this one. Hope you enjoyed it, and we'll see you in the next one.